So why do we talk about all that history stuff? Well, let's just give us an idea of the importance of atomic theory. So the atomic theory is the idea that all matter is composed of atoms. It grew out of some observations and laws, specifically these three: the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. And we'll talk about each of these. So the law of conservation of mass says that in a chemical reaction, matter is neither created nor destroyed. And this came about from the work of Lavoisier. We talked about him in the first chapter. He liked to burn things in closed containers. And when a chemical reaction occurs, the total mass of the substances involved doesn't change. And if we think about Lego blocks or Lego bricks, now they're blicks. I just made up a new word. If you think about Legos, and you take a Lego structure, maybe a spaceship, right? And you put it on a scale and you measure how heavy it is. And then you take that apart, you take the blocks apart and you put them together and you make two smaller spaceships. And you put the two smaller spaceships back on the scale. Has the mass changed? No, because it's the same blocks. All the blocks that were there before are still there. That's how chemical reactions work. The atoms don't change. All that changes is how the atoms are arranged and connected to each other. So atomic theory says the particles rearrange during a chemical reaction, but the amount of matter, the mass, is conserved because the particles themselves are indestructible. So an example here, illustration and photograph. So here we have a picture of sodium metal. It looks like a metal, it's shiny, but it's actually much softer than most of the metals we're familiar with. You can just cut it with a regular table knife. And here we have an illustration of what the sodium atoms might look like in that solid. So here they're depicted as purple spheres. Here we have chlorine gas in an Erlenmeyer flask. Chlorine gas has kind of a yellowish color. It's toxic, it doesn't smell good. And if we were able to zoom in and see what composed that, we'd see that the chlorine is composed of little molecules, each having two chlorine atoms. Here they're depicted as green circles. When we put these two things together, they react chemically and form table salt, sodium chloride. So here you have chlorine gas, very toxic. Sodium metal, not specifically toxic in itself, but it reacts very violently with water. So if you ate it, you'd get an explosion basically in your mouth, so not good for you either. And you put them together and they make table salt. Now obviously too much salt is not good for you, but a little bit is actually required for you to stay alive, right? You need table salt. And the table salt looks like this. It's a repeating pattern of sodium and chlorine atoms. But when you combine these two things together, all of the purple and all of the green spheres that were originally present are still present. And so if you choose your amounts carefully, here weighing out 7.7 grams of sodium, 11.9 grams of chlorine. When you combine those together, you can predict what the mass of the salt is. It's the sum of those, 19.6 grams. So the mass before and after doesn't change. Any questions? So here's a question, conceptual question. When a log completely burns in a campfire, the mass of the ash is much less than the mass of the log. What happens to the matter that composed the log? Three choices here. A, the matter that composed the log reacts to form gases that are released into the air. B, the matter that composed the log is converted into energy. Or C, the matter that composed the log is still present in the ashes but has a much lower mass. A. So the reason that we are seeing that what's left in the campfire weighs less is not because the matter weighs less or that the matter was changed into something else, but much of that matter floated away into the air. So the carbon and hydrogen that were part of the cellulose in that log combine with oxygen in the air and become carbon dioxide and water vapor, and they float away. So it's not that the mass has changed, it's that we don't have all the mass anymore. And that's why it was so significant that Lavoisier burned things in closed containers, because then those gaseous products couldn't escape. Another law of importance here is called the law of definite proportions. And this says that all samples of a given compound, regardless of their source or how they were prepared, have the same proportions of their constituent elements. So this was formulated in 1797 by Joseph Proust, a French. There's a word missing there, a French chemist. So the example is, if you take 18 grams of water and decompose it into carbon and hydrogen, you'll get 16 grams of oxygen and 2 grams of hydrogen. And so you can look at the mass ratio of those elements. 16 grams of oxygen to 2 grams of hydrogen, that ratio is 8 or 8 to 1. So by mass, there's 8 times as much oxygen as hydrogen in this sample of water. The law of definite proportion says that that proportion is true for all samples of water, regardless of where you got it, from the King's River, from the Nile River, from the outer atmosphere, whether you created it in the lab. It's always an 8 to 1 mass ratio of oxygen to hydrogen. So the mass ratio of nitrogen to hydrogen in ammonia is 4.7 to 1. We shouldn't remember that or know that, it's just telling us that. So if a sample of ammonia contains 10 grams of hydrogen, how many grams of nitrogen does it contain? So what this is saying is that there are 4.7 grams of nitrogen for every 1 gram of hydrogen. We don't need a calculator for this because the numbers are chosen to be nice. So if we have 10 grams of hydrogen, the question is saying, how many grams of nitrogen do we have? 10 times as much, right? So instead of 4.7 grams, we'd have 47 grams of nitrogen. So you take the elements that are in the compound and you separate them and weigh them. The ratio by mass is the same. Whether you started with a little sample, big sample, no matter where it came from, the mass ratio is the same. Any questions? Here's an actual problem that we might have to do some math with. So when you do these early problems, I know that you've taken a chemistry class as a prerequisite to get here. And so you know about stoichiometry and molar masses, and you have this at least vague memory of all those things. We don't need any of that here, okay? So we're going through, we haven't talked about any of that, and so the book is assuming that you don't know about that stuff, and so we can solve these problems just with the idea of definite proportions. So this says 2 samples of carbon monoxide are decomposed into their constituent element. One produces 17.2 grams of oxygen and 12.9 grams of carbon, and the other produces 10.5 grams of oxygen and 7.88 grams of carbon. Show that these results are consistent with the law of definite proportions. So what does the law of definite proportions predict about these ratios? They're going to be the same, right? So how do we show that? Well, we calculate the mass ratio. So here we have one sample that has 17.2 grams of oxygen for 12.9 grams of carbon. And then we have another sample with 10.5 grams of oxygen for 7.88 grams of carbon. This one does require a calculator. So 17.2 divided by 12.9 and this is 1.33, and the 3 is repeating, it's 1 1/3. If I use my rules of significant figures, each of these numbers has 3 significant figures. These are measurements, they're not perfect exact numbers. So 3 and 3, then this number should have 3 significant figures, so I'm going to express it as 1.33. Then the other one, 10.5, divided by 7.88. This one should also end up with 3 significant figures. The digits after that are different. This is 1.33248731. But based on the precision with which these measurements are made, those ratios are the same. The ratios are the same because it's the same compound. Any questions? Then we get the law of multiple proportions, which just on the surface seems to contradict the idea of definite proportions. But here we're not talking about the same compound, we're talking about 2 different compounds. And this one is a bit hard to explain concisely in words. So we're doing our best here, and then we'll talk about it, and hopefully it'll become a little clearer. So when 2 elements, we're just going to call them A and B, when 2 elements form 2 different compounds, the masses of element B that combine with 1 gram of element A can be expressed as a ratio of small whole numbers. And this was published in 1804 by John Dalton. The idea here that in a compound, if you have 1 atom of A, it could combine with 1 atom of B, or 2 atoms of B, or 3 atoms of B, but you can't combine with like half an atom, right? It has to be entire atoms. And so if we take the ratio of the 2 ratios, we get a small whole number. So the masses of B that react with a certain amount of A are related to each other as small whole number ratios. So let's look at how that would work. So carbon and oxygen form several different compounds, but 2 of them are carbon dioxide and carbon monoxide. So each of these has 1 carbon atom, this one has 2 oxygens, this has 1 oxygen. And if we look at the mass ratio here, we find that 2.67 grams of carbon will combine with 2.67 grams of oxygen combines with 1 gram of carbon. In carbon monoxide, it's 1.33 grams of oxygen per gram of carbon, right? And so we look at that and we say, well, those ratios are different. Yeah, this is not the law of definite proportions. These 2 things are not the same compound. If they were the same compound, their ratios would be the same. The law of definite proportion says if we take this ratio and divide by that ratio, so that's what we're doing here, 2.67 divided by 1.3, we're going to get a small whole number. So here we get 2. And what that says is that the carbon dioxide has twice as many oxygen atoms as the carbon monoxide atom. And so we can use the masses to help us identify how many atoms of each element are present, even though they're way too small to be seen, and we can't look at them. But we can use the masses to learn about the compounds. And these ideas, this was published in early 1800s. That was well before the discovery of electricity, right? Science was very primitive at that time, and yet they were able to discover a lot of really, really cool stuff. So here's a law of multiple proportions problem. So hydrogen and oxygen form both water and hydrogen peroxide. The decomposition of a sample of water forms 0.125 grams hydrogen to every 1 gram of oxygen. The decomposition of a sample of hydrogen peroxide forms 0.0625 grams of hydrogen to every 1 gram of oxygen. Show that these results are consistent with the law of multiple proportions. So our first sample, we have 0.125 grams of hydrogen to 1 gram of oxygen. And the second one is 0.0625 grams of hydrogen to 1 gram of oxygen. It's the amount of hydrogen combining with the same amount of oxygen for each thing, right? So these are the two numbers then that we're really interested in. What does the law of multiple proportions say about those two numbers? How are they related? They're related by a small whole number. Some of you can look at the numbers and recognize that 6 1/4 times 2 is 12 1/2. But I wouldn't expect everybody to be able to do that. How can we identify this? Just take the larger number and divide by the smaller number. And we should get a whole number. It doesn't always come out perfectly. If you're using real measurements, it might come out to like 2.09 or something, or 1.99, a little bit off of exactly 2, but it's really, really close. And if you measured more precisely, you would get closer and closer to 2. Any questions? So John Dalton explained the laws, conservation of mass, definite proportions and multiple proportions, with his atomic theory, 1808. So theory explains, the law just says what happens. So this is his theory. Each element is composed of tiny indestructible particles called atoms. All atoms of a given element have the same mass and other properties that distinguish them from the atoms of other elements. Atoms combine in simple whole number ratios to form compounds. Atoms of one element cannot change into atoms of another element. In a chemical reaction, atoms only change the way that they are bound together with other atoms.
It's crazy you can figure all that out in 1808.
Exactly, it is. It's crazy that he could figure that out in 1808. I mean, it really is mind-boggling. And you go back, if you look at the history of science, it's really, really fascinating. So today we have overwhelming evidence for the existence of atoms. Back then, though, this was a new idea, and this was a big, big deal. Now, what do you think about all those things in this theory? Do you think all those statements are absolutely true? Are atoms indestructible?
Well,
Have you heard of atom smashing?
I've heard of atom splitting.
Atom splitting, yeah. So it turns out that atoms are not indestructible. But can you destroy an atom in an ordinary chemical reaction? No. Can you destroy a Lego brick? Yeah, see? Lego brick playing with it in a normal way? No. What if you get out a hacksaw? Can you cut the Lego brick in half? Yeah, you can. But that's kind of extreme, isn't it? So there are a couple of things in this theory that were later found to be maybe not true all the time. And does that mean we throw the theory out? No, it just means that we revise the theory. Now, statement 4, as it's stated here, does have that limitation. What's wrong with my pointer? There it is. In a chemical reaction, atoms only change how they're bound together. Turns out, in a nuclear reaction, you can change one element into a different element. But that is a very separate thing. There's one other statement in here that is not quite true. It has to do with mass. Do all atoms of a same element have exactly the same mass? No, they don't. And we'll learn about that in a little bit, isotopes.